Welcome to this session about some fantastic technique about the AI. So, this session is about how the machine learning and AI changing the world of satellite data in decision making on air quality and environmental health. We have two HAQAST members and two stakeholders. So let's welcome our first presenter, Bryan Duncan from HAQAST.
Good morning. Okay, so I'm Bryan Duncan, and I'm presenting on behalf of Dan Anderson and Amir Suri. They're two people I work with at NASA. Dan's a HAQAST team member, and Amir is doing some work that's very relevant to HAQAST, but neither of them can be here. They're both out of the country right now. They're both the brains and the bronze of these projects. It's not me, I'm not an expert in machine learning, but working with them over the years on these projects, I've learned quite a bit about machine learning and the potential for or the type of work that we do. Where am I supposed to be pointing? Okay, so air quality folks see ozone data from their air quality monitors as ground truth, right? But these monitors are sparse in space, spatially. So they use other tools to fill in these gaps, such as air quality models and satellite data. So they have these extra tools. But the problem is these air quality models are oftentimes biased in their ozone predictions, and air quality, the satellite data, it's not nose level, doesn't give you nose level concentrations. And it does, and the ozone observations are primarily the total ozone column, but Tempo does have the promise with one of these new products to give you closer to the surface. Are you doing it for? Can't seem to make it work. Okay. So what I'd like to do here is to introduce three new tools that we've been working on that hopefully will help air quality managers, three new tools for their toolboxes. And all three of these are machine learning based tools. And all three of them are taking advantage of this wonderful tempo data. So let me walk you through each of these tools. You're doing it for me. I can't, this thing doesn't work. Okay. So the first one is directly constraining ozone. So this is Dan's HAQAST project. This is what he proposed. And what he's doing is he's using tempo data. This is tropospheric columns of NO2, formaldehyde, as well as the total ozone column. And that gives you the information on the photochemistry of the sunlight, the amount of radiation getting down to the boundary layer. And he also uses information from a high resolution MET model, HRRR, and then other things he's trying to work with are population density, road density, and so on. He's using gradient boosted regression trees, and his training targets are the air quality monitors, these surface monitors from EPA. And he holds out a certain number of these to do validation. Okay, next slide. Okay, so overall, the results are pretty promising for this is preliminary work. He's gotten some really good initial results. The R squareds are about 0.7 for these holdout points. That's not bad. You can see there's some other areas that the correlations aren't particularly good, and he's starting to work on that to figure it out. And this is one site at the University of Wisconsin-Milwaukee. And you can see that the ozone from the EPA monitor and the tempo derived data set are pretty good. So we feel like, yeah, there's a lot of promise here. Not all of the sites look this good, but a lot of them do. One thing you'll notice here is that this machine learning model as it stands now is not getting the high levels of ozone during the seeding stage. And Dan has some ideas about how to improve that, so we'll work on improving the model. Next slide. Okay, so how is it doing with regional variations? So first of all, Dan is trying to learn how to do these plots in Python, and it's an ugly plot. It's not very good. So he apologizes. But what this is North Georgia, and in the box here is the Atlanta metro area. And each of these circles represents an EPA site. And I know it's almost impossible to tell from the audience, but the actual observations are colored in these circles. Next slide. Okay, so what you can see, the take-home message here is that at the different times of day, the machine learning model is doing a pretty good job at reproducing the spatial distribution of what's being seen at the EPA monitors. Next slide. Okay, so this is the second tool. This one's more mature. This is from Amir Suri. And for the last 15 years, air quality folks have been using satellite data of the formaldehyde to NO2 ratio to get an idea of ozone production sensitivity. And that's based on, that serves as a proxy for the VOC to NOx ratio that air quality folks have been using, I think, since the 1970s. But the one thing that's a problem with this formaldehyde to NO2 ratio is ozone production isn't only dependent on those two things. There's also other factors that are important, like sunlight and water vapor, for instance. Next slide. So what Amir did is he wanted to take all of this into account, and he used deep neural nets to parameterize the surface ozone production and to get at the chemical sensitivities to NOx and the VOCs. So I recommend that everybody check this out, because that's his website, and it has data from Tropomi and OMI on there globally. It's a really cool site. I spent way too much time playing around with it. He has a lot of great plots on there, lots of just wonderful data. And I'll just show you one thing that he did here. Is he was, as you all know, NOx has really decreased over the last 20 years in the US. So when he's doing trends of his ozone production, you see a lot of blues in the cities. That's going down, as you would expect, but he was finding reds in the areas of oil and natural gas exploration, including the Permian Basin, as well as, I think that's Eagle Ford, south of San Antonio. Next slide. Of course, everybody's talking about tempo, so Amir made these plots for us of tempo. It's time of day, so the first column here is the ozone production, and then you have the sensitivity to formaldehyde in the middle column and the sensitivity to NO2. So this is work that he's trying to finish up now, so that we can get a better idea of how his data, how his product will be applicable to tempo and give us information throughout the day. Okay, next slide. Finally, hydroxyl radical. That's not ozone, but it's very important. It's central to so much of the atmospheric photochemistry, and we have very sparse observations of this. So in our air quality models, OH is all over the place, and it's a real problem. So how do we do a better job at constraining it? Dan is trying to do this with satellite data machine learning again. Next slide. So to try to get a better OH to constrain these air quality models, he's using, again, GBRTs for the tropospheric column OH. And this is early days, so he's already done a proof of concept demonstration here where he has trained the model on an air quality model from NASA. And he's input all of these different satellite data products, including NO2, formaldehyde, CO, the overhead ozone column, and water vapor. So he has this long 20-year record, and it looks really great. But one of the problems is we see these trends here over this period in OH over the oceans. But what's driving these trends? So you can use things like SHAP values to try to get an idea, see which of the chemical inputs are driving the trends. But from my experience working with them, sometimes it makes sense, sometimes it don't make sense. So I don't know exactly what we're getting out of it. Next slide. So how do you make the machine learning models more process-based? Because they're not necessarily process-based. It's just a fit, right? So when you look at trends or trying to interpret trends and variability, you don't exactly know what you're getting. So one is to, well, we can try to constrain with multiple tools like we've done here, add more tools in so we can get a better, more comprehensive picture of what's going on to understand the causes of trends and variability. The other thing, which we haven't done yet, is there are newer machine learning models out there or techniques such as process-informed neural nets. That could be one way to do it. And then third, the way we ended up tackling this problem of what I'm calling interpretability is we're not constraining, say, just ozone or just OH. We're trying to constrain individual processes. For instance, with the OH model that we did, we're constraining the individual source and sink terms, the chemical terms. So there are ways that we can improve this and get more process-based information out of it. Next slide. Okay, this is my final slide. So we have, for each of these products, as I said, some are preliminary, some are more mature, but we've got a lot of work ahead of us. For instance, for the OH work to apply it over land, where it's much more complicated with all the VOC chemistry, and especially working to try to constrain OH in urban environments, for instance. So I recommend that, again, you go to Amir's website, which is really cool. Click on the Browse Maps. I spent way too much time there. And if you have any questions, you can always reach out to me and contact Dan and Amir. Their emails are here. And for the air quality folks in there, we really need your input to make these data products available and make them in a way that's useful for you all. So please, if I said anything that's piqued your interest, reach out to us.
Thank you, Bryan. Okay, thanks. Then let's welcome our second speaker, Elise Penn, from one of our stakeholders, I say.
Hello, I'm Elise. I'm working with ZeusAI, and I wanted to start by saying that I've actually been part of the HAQAST community. I've been lucky to be part of the HAQAST community for most of my career. I started all the way back in 2017 when I was an undergraduate at UW-Madison. I attended my first HAQAST at Columbia. At the time, I was working on a project to understand what we would see from this upcoming satellite called Tempo. You may have heard of it. After that, I was inspired to go do my PhD in atmospheric chemistry at Harvard, where I took a bit of a detour and focused on inverse analysis of methane. And then that interest in inverse analysis got me interested in AI and machine learning methods. And so now I'm at a company called ZeusAI, which I'm going to talk about today. I'm going to talk about what we do at Zeus and also our upcoming observation to observation regional air quality model. So Zeus is a company that's focused on building AI models for Earth observations. We specialize in low latency weather products and analysis products, but now we're getting into air quality applications. And we're supported by the SBIR program. So for people who don't know what that is, that's the Small Business and Innovation Research Program. And the goal of that program is twofold. It's first to spur private industry to develop research and development projects that for technologies that are useful for the federal government. And then also to encourage private industry to sort of export the technologies that we've developed in the federal government to private industry. And so that second goal is very well aligned with HAQAST, the goal of getting, we have all of this data. It's all in level 2 columns that are hard to access. How do we get it into a product that is actually useful? And our two co-founders are TJ and Kate. They've spun the company out of NASA Ames in 2022. And the rest of us have joined about 6 months ago. So the question that we are trying to tackle at Zeus is very similar to what many people in this room are trying to tackle, which is that we have more satellite data than ever before. We've seen this figure before. This is just the NASA Earth fleet. And it produces hundreds of terabytes of data per day. That's more data than one person could ever comprehend. So how can we use all of this data? And so at the same time, there's this revolution that's happening in the world of weather forecasting, which is that the machine learning and AI weather forecasting models have now improved to where they're better than the traditional weather forecasting. However, under the hood of all of these weather forecasting models, they still rely on the data assimilation products that are produced with traditional methods. So all of these models are trained on typically ERA 5 data. It's a nice 20-year data set. It's completely gap-filled and consistent. But at that first time step, they have to wait 4 hours for traditional data assimilation to run. And that's because this is a much more challenging problem. As everyone in this room is familiar, satellite data is noisy, it's sparse, it's really difficult to work with. And as a result, only 5% of satellite data that ECMWF receives is actually assimilated into their weather forecasts. So there's a lot of data out there that could be being used. And so the goal of Zeus is to create data assimilation products that bridge this gap and make the data easier to use and more powerful. So we currently have, 3 products and then our upcoming air quality model, which we just started development on a few months ago. So the first is our flagship model, EarthNet. And this is a multimodal AI model, which can assimilate satellite and surface observations. Then we have Helios, which is our solar model. We have a stereo wind vector product, which takes two geostationary satellites and can get altitude and wind direction. And then the regional air quality product, which I'm going to talk about progress towards today. And then I wanted to flag, if you're interested in the data that we produce, our historical data for Helios and the stereo wind vectors is available for free at the Earth Mover Marketplace. So that provides basically an API so that you can download the data pretty easily. And then in general, for the scientists in this room, if you're interested in Zeus data, talk to me. We can usually provide, especially historical data, for free for non-commercial use. And if you're commercial, we can provide demo data. So I'm going to focus on EarthNet for a few seconds because that's what we're going to use to assimilate tempo data. And the way that EarthNet works is these are all IR radiances from different satellite products. So here is GOES. And what we produce out is actually, this is a little bit different paradigm than traditional modeling, but what we produce out are gap-filled satellite products. So if you input GOES satellite data, you output a gap-filled GOES product. And so, for example, GOES is only available over the Americas, but because we have data from VIIRS, we can produce a gap-filled product, which produces a GOES-like product over the poles. And so that's very high level what EarthNet does, and then I'm just going to summarize, like high level, go through how it works. So the way that it works is we take in the satellite data and we first have to compress it, and we call this tokenization. And the reason we have to compress it into tokens is basically because this is so much data. It would be very hard to train a model on this much data, so we need some compressed representation of the data first. And then we use a masked autoencoder to gap fill the data globally. So what this means is that to add a new product to EarthNet, we simply need to tokenize it and incorporate it into the model, which makes it easy to extend to other data sets. So I'm going to talk about our progress towards compressing tempo satellite data. So this is the original tempo observation for 1 hour. And then this is the reconstruction from the compressed tempo data. And as you can see, they look very similar, but this is just one time step. So when you look at the global statistics, you see that we have like less than 1% error and a high correlation, which is great. It looks like the tokenizer is working and we're able to compress the tempo data. But I wanted to point out we are using tempo version 4, and there's been a lot of discussion of version 3 versus version 4 in this conference. And so we actually originally tried to work on tempo version 3 because there wasn't very much version 4 available a few months ago. And we had a very hard time compressing that data. So again, the tempo observation and the tokenizer reconstruction look almost identical, except for we're missing some data because of our interpolation process. But the R squared is only, or the R is only 0.7, and we're not really able to capture the variation in that data. So I just wanted to highlight this because it points out like how important it is to have high quality satellite data if you're building these kind of data-driven models, because you're limited entirely by how good your data is. And then finally, so the ultimate goal of EarthNet. So we've been contracted by NASA to build EarthNet, and we work with NASA Power. And the ultimate goal of incorporating tempo into this product is to create a gap-filled tempo and surface product every 15 minutes at 6-kilometer resolution. But I just wanted to highlight some of the differences in this model because I've seen a lot of really great work at HAQAST, which involves AI models. The main difference is that we're trying to bring together multiple modalities in one, the GOES, tempo, and station observations. And then also needs to be predictive, so it should respond to perturbations. So in particular, the application, which we're focusing on first, is that if you add a location of a fire, it should be able to predict out smoke. However, we'd like to hear from this audience how you would use this data set, if there are any applications you would be interested in. And then also I'm noting again that we can provide it for free once it's available to non-commercial users. So thank you so much for your attention, and I'll take questions after at the panel.
Thank you, Elise. Okay, let's welcome our next speaker, Nathan.
All right, thanks. So I'm Nathan Pavlovic. I'm lead geospatial data scientist at Spheros Environmental, until very recently called Sonoma Technology. And today I'm going to talk a little bit about AI and machine learning in air quality and environmental health. And in particular, I want to talk, I'll start with some highlights of applications, a couple of projects where we've used AI and machine learning that I think highlight some of the directions and thoughts. And then I want to kind of, at the end of the presentation, talk a little bit about some of the overall takeaways from that work and what it means for how we make decisions using AI and machine learning, and how the community might advance going forward with using that, and some of the opportunities and limitations of doing so. Yeah, so a couple of projects that I've been involved in. One, actually a couple, this one and then the next slide, were led by Rima Habra at USC, and we had a hand in this work. And the first was an application looking at satellite data gap filling. So we were interested in incorporating satellite data into exposure models, but we experienced the limitations of having missing data. And so as a part of this work, we developed an autoencoder representation that used ensemble methods and deep learning to first downscale predictive data sets and then ultimately gap fill MODIS MIAC AOD data. And then that was able to feed into subsequent analyses that I haven't shown here, but starting to use some deep learning. Actually, no, I have, so it's here, this is, this slide has it. And so that then was an input. The AOD, gap-filled AOD was then an input to this additional work that Leo Lee led, again at USC, using ensemble-based deep learning to estimate PM 2.5. And one of the things that we worked on there was specifically incorporating predictors of wildfire smoke, which is one of the main drivers of PM 2.5 within in California and increasingly across the United States. And so this was another area where we're using neural network architectures or deep learning to start trying to produce high resolution outputs in a continuous way to understand exposures to PM 2.5. On the right, then, is a recent paper out last year where we extended this further, specifically using knowledge-informed deep learning architectures. And so these are architectures where you're trying to represent, you can maybe see some equations up there in the right-hand corner, where we're trying to represent the actual physics and chemistry inherent to these pollutants, in this case applying it to NOx and NO2 and nitrogen oxide, and really trying to understand how what are the physical constraints, and then represent those within the architecture of the model itself. And we showed that in that paper, Leo was able to show really good performance coming out of that, and some improvements over previous efforts by incorporating that physical representation into the model. Wildfire smoke is a big theme. It's how I got into air quality originally, and is something that I'm very interested in. And so I wanted to highlight some ongoing work as well, looking specifically at wildfire smoke impacts and developing machine learning based high resolution smoke exposure data sets. And so we'll look at this case study. So for those who are in the Bay Area or may have heard about this in the news, on September 9th, 2020, San Francisco was inundated with smoke that caused the sky to turn orange. It was like in the news called the Orange Sky Day. Orange Sky Day, but actually this was about 5 days from September 9th to the 14th. And you can see in the GOES image there on the right that not only San Francisco, but much of the state was inundated by smoke, both coming from local fires, relatively local fires in California, and then also transport from the fires up in Oregon, where the smoke went out over the Pacific Ocean and then was transported back to the coast and ultimately to San Francisco. And so that, of course, showed up in the regulatory monitoring data as a spike in September 2020, although we saw the main impacts, or the really like compelling impacts, on September 9th. There are actually multiple spikes of impacts during that time period. And so what we wanted to do was provide, or develop a high resolution estimate of the wildfire specific component of PM 2.5 that impacted people in San Francisco during this time period. And so what we've done is developed a data processing flow that incorporates both the reference grade monitoring data and low-cost sensor information from the Purple Air Network, which was already quite dense in San Francisco and became much more dense actually during this event as people started becoming very concerned about their air quality and deploying Purple Air sensors. And so we combine those two sources of data, and optionally, and we've been experimenting with bringing in high split modeling with the satellite-derived wildfire emissions, and also using the GOES aerosol optical depth data directly, feeding those into machine learning and geostatistical fusion model to attribute the portion of smoke of PM 2.5 specifically coming from smoke. And what you can see is in the figure on the lower right is the results of that fusion. The native resolution is hour by hour. We're showing daily averages here. And you can see that the smoke really rolling into San Francisco on the 9th and 10th, moving west to east, persisting through the 14th, and then dissipating onto the 15th. And although we're looking at the Bay Area overall, this is our full domain for this initial effort. If you zoom in, you can actually see variation, really on a very fine scale resolution, and that's primarily driven by the use of the low-cost sensor data. One of the things that I'll highlight here, and I'll come back to it at the end, is the box there that says quality assurance and calibration. And in using the low-cost sensor data, that's actually one of the biggest efforts here in this work, is making sure that we can trust the low-cost sensor data and use it reliably. So we have a paper that's, I'm working on revisions currently, where we've developed a process for validating the data. We've used some of the well-reported approaches in the literature, and then also developed a distance-based evaluation method comparing reference monitors to the low-cost sensors in situ to identify issues. And we actually found a case on September 13th and 14th where there were large deviations between the purple layer and reference monitors that was, we believe, driven by that long-range transport and some of the transformation of PM 2.5 during that period. So the point that I'll come back to is that data quality, even in these machine learning and AI applications, remains critical, and there's a lot of work there that needs good attention. I wanted to touch quickly on some other work that I've done using machine learning combined with air quality, and this was specifically looking at the impacts of air pollution, specifically nitrogen and sulfur deposition on tree species using a machine learning algorithm. And so what this work really highlights in terms of applications is the use of model interpretation techniques, specifically the partial dependence plots from the machine learning models, to understand how particular variables influence outcomes. And specifically, we're looking here at how nitrogen and sulfur, we were using the machine learning models to interrogate how the nitrogen and sulfur deposition impacted tree growth and survival for tree species across the United States. And so you can see one of the key things that we were able to do by leveraging the power of machine learning, we were able to build these bootstrapped ensemble models that allowed us to understand the uncertainty in the results that we were seeing, which provided critical context for ultimately using this data in regulatory decision making. And then recently, we've also extended this work to understand ozone impacts on trees, tree growth and survival, and then also further dug in using, again, the model evaluation and interpretation techniques to understand not just these national level sort of average impacts, but actually localizing the response of the trees to this deposition based on mediating factors. So a tree might be more sensitive if it's in a particular climate or growing in a particular type of soil, and we're able to account for that, again, using this modeling technique. So those are a few cases where we're using our AI and machine learning to understand air pollution and ultimately drive decision-making to protect people's health and the environment. And I just wanted to wrap up here with a couple of thoughts about considerations. Where is this all going? How is it going to impact decision-making? And what should we be thinking about as a community? And I first wanted to just highlight a few emerging directions that we're thinking about, many of which I've touched on, some of which I haven't, but wanted to start with knowledge-informed models. So the work that, again, at USC was leading has led using models that can specifically represent physical processes, I think is actually very important. We've seen some papers out from the weather modeling side and elsewhere that have shown that some of these emulators or other model types may fail or may not perform as well as expected in extreme cases. And by building in physics, there's potentially opportunities to try and address some of those limitations. Model interpretation techniques allow us to interrogate these models. I think they both address an issue around trust because it allows us to understand what these models are doing, and it also gives us an opportunity to ask new questions about the relationships between variables within the data sets we're looking at. LLMs and multimodal models, I think this is a very interesting direction. People are starting to use, have been using and continue to use LLMs for everything from data analysis to coding, but also to start looking at, can we connect LLMs to physical models and start asking questions directly in a natural language setting? And that's a really interesting case. The UN has a beta product called Environment GPT. That's just one that I've seen over the last couple of years that I think is really interesting, where they've linked up their data, their documents to a chatbot, and you can, or an AI agent, not agent, an LLM, and you can go and ask questions, and it'll give you information about environmental impacts that are summarized by AI, but tied back directly to references within the UN corpus. And so this is a way that we're starting to see people address issues around hallucinations and unreliable information. Foundation models and digital twins. I think the speaker from Zeus really highlighted those applications around foundation models and how those are exciting. And then the physical model emulation can potentially increase modeling speed, and which either makes things cheaper and easier to run, which is exciting in sort of a democratizing sense, or it means that we can do more in terms of probabilistic modeling and ensembling. There's a lot of challenges in this space as well, though. Transferability, can you take a model that's developed on data sets that are really dense and useful in North America and apply it, say, to South America? I think that's a big challenge. There's a lot of challenges around trust and validation. I think these models in many senses remain black box. I don't think that's necessary, but it's certainly the case that you need a lot of technical capability and compute power to start getting into the models and understanding what they're doing. And so we need better frameworks for trust and validation. There's a question about equity. Does this help democratize access to air quality information and produce more information, or does it mean sort of increase the divide between the haves and the have-nots? And then I think, how does that all then feed into action and decision making? Can we actually improve the way that we're managing air quality? Can we bring down air pollution concentrations based on this? And I think that's the thing that we need to tie it back to, because there's lots of really exciting, cool things we can do, but we need it to be useful so that people improve health. Last thing, just to say, again, the input data is so important here. It really is still, garbage in, garbage out. And so the data quality, quantity, and representativeness are critical. And I just wanted to highlight one other project that I'm involved in that's being led by NRDC, OpenAQ, and Sonoma Technology, now Spheros Environmental, to build an open source data management system for researchers, communities, and governments that are deploying sensors and undertaking their own monitoring campaigns. This data management system allows you to bring in data sets from multiple sources and perform either automated or interactive quality assurance, and then use that data for downstream pipelines. So I'm really excited from an AI perspective to be working on building out this tool that will allow people to do more, to collect, quality assure, and ultimately produce data that can feed into these kinds of applications that hopefully are more representative and higher quality. So I'll stop there. Thank you very much.
Thank you. Let's welcome our last speaker, Pawan Gupta from HAQAST team.
Thank you. So I'm going to talk about some of the data sets and application we have been developing over several years as part of previous HAQAST and this HAQAST, and we're using AI/ML approach to do that. So I'll start with this broad picture, which probably you have seen thousands of times. We use this hybrid approach where we're trying to combine the data from models, ground measurements, and satellite observations. So the model provides us like a geophysical interpretation, the way to how the processes works in the atmosphere, right? The state of atmosphere. And then the satellite observation give you a near real time, what is happening in the atmosphere right now, right? So you have a observational perspective from the satellite. And then the grounds, they are limited in terms of the number of measurements. They are very less dense, as we have seen in many, but they are the ground truth. They provides you an anchoring point to validate and to evaluate your satellite data, to your model outputs or AI-based any product. So we use all of these three together. I just want to emphasize that we use NASA's GEOS FP and MERA-2. MERA-2 is a reanalysis. FP is runs in a forecasting mode. And the advantage of using GEOS FP is it assimilate the aerosol satellite data from MODIS, and they are starting from the VIIRS now. So there is another model, NASA runs GeoCF, which is really great for trace cases, but for aerosol, they don't actually assimilate yet the satellite data. So that is why we are sticking with the GeoCFP. It gets updated, and we are aware of the problem, and we continue to actually evaluate. And so far in last 7 years, I haven't seen any noticeable difference in terms of our machine learning algorithms. So. Okay, so this is first of the application or forecasting product which we developed. It has started in last HAQAST cycle. This is in partnership with Department of State. As you probably, most of you are aware of that Department of State through their US embassies all around the world used to monitor air quality PM2.5 using a reference grade monitor in partnership with US EPA. There were about 80 sites used to be there. Unfortunately, last year, the program got closed. Uh, so we have a long partnership with them. We're still working with them to provide air quality information as well as forecasting, because even if their monitor were on, they don't have forecasting capabilities. So this project was started in that way. And what we are doing here is we are taking GEOS model as input, bias correcting it with the ground measurements wherever we have available on the ground, reference grade, and then providing 3 days forecast for every 3 hours. So this started with 10, 15 location as US embassies, with the help of additional support from NASA's Satellite Need Working Group. We were able to expand this actually to 10,000 plus location, which covers all OpenAQ sites, which cover all Aeronet sites, which covers all US missions abroad, and then about 1,000 cities in Africa, because we are focusing this time around Africa. So this data set is available on that website. It is also available through an API. So if you want to port the data on your own application, you can actually use through API. So this is just giving you a flavor of how the results looks like from this forecast. This is a single site. It's showing 3 days forecast, and also the black line shows what the ground measurement is showing. So this is just a cherry picking of one station. But if you look the scatter plot on the right side, where we have independent validations performed over many stations, and it really looks actually too good to believe, right? So especially I'm excited about those high values. If you have seen many of the machine learning model, it has challenge in actually getting those extreme high values correctly. But we have done some machine learning technique, and Junhyun, he is not here, but he has published 2 papers. So if you are interested in like technical details, more validation evaluation, please refer to these 2 papers, and we can talk offline also. Okay, so there is another attempt which we are doing since. So just to clarify, this cycle we are focusing in Africa, and we are trying to develop some products for Africa which can be used. So forecasting is one, but then we also want to do the real-time monitoring, right? So there is a series of geostationary satellites like GOES-R, Meteosat third generation, Himawari, AMI. So these, if you combine these geostationary satellites all over the globe, they are able to provide you every 10-minute global observations of aerosols. Okay, and they are really advanced. Their accuracies are very high. The spatial resolution is very high. So there is an effort, something called GeoRing, where we are trying to combine all the satellites. But in this specific study, we are using the Meteosat third generation, which was launched, I guess, in 2024. And the data has started becoming available very recently. They do not have a official operational aerosol optical depth product yet. So what we're doing here, our end goal is to get a PM2.5 hourly product. We did a similar study over US where we used the GOES-R and did a bias corrected PM2.5, and it was delivered to US EPA, and it is actually, they are using it. So we're doing the similar thing here. We are using FCI, which is a sensor on Meteosat third generation. First, we are using Aeronet to actually get the aerosol optical depth, because it has more application than just the PM2.5. And then, so the initial results looks pretty good. This is only 1 month of very initial data analysis. Again, the machine learning is able to really produce very high accurate data. And if you compare that with some of the readily available satellite data, for in this case, we have Weir's map on the left, and on the right is the FCI derived about 5 over mean. So one of the advantage of using the geostationary here is that you have every 10-minute measurement. So if you actually combine the data from several hours, you on a daily basis, you will get a good gap filled data set. So the cloud cover effect will be minimized because we have frequent measurement. So ultimately, our goal is to get a PM2.5 map on a hourly scale. So this is a ongoing work. Okay, so next what we are trying to do is we have all this forecast, we have historical data, we have monitoring. So we want to put this all the information in some kind of AI agent. We are in 2026. We all use AI agents for all our daily lives and professional lives, right? So we thought, why not we put something so that this AI chatbot can talk to our data? So what is the difference between this AI agent and ChatGPT or Gemini? I mean, if you type any information, any question on Gemini or ChatGPT, it will give you an answer based on some search on internet, right? The advantage here is it is tied with our data sets, which are validated, trusted, and peer reviewed. So any question you put about air quality, it will go back to the database, retrieve the information, and if it is relevant, if it is able to find, then it will provide you an appropriate answer. If it is not available, then it will say it's not available in our database. We can look for on internet search and so on. So this is a very fresh alpha version. We are just testing. We are going to test with the World Bank and Epic team. It's available both as a web app and the WhatsApp. So this is something, a new development we are trying. Okay, ultimately we want to put all this together into a one-stop shop. We are calling it African Air Quality Explorer. Why we are doing this? Because as I mentioned earlier, we are started with the partnership with the US embassies. They need the information in many of these countries, but then also there's a lack of resources and availability in Africa overall. So we are trying to fill that gap. Our vision for this tool is very simple, easy to use online tool where you can actually get all the information in one place, which has historical data, real-time data from Meteosat third generation, forecasting, and on top of that, some analyzing tools which you can use. So again, this is on developing a stage. And lastly, I just want to acknowledge all our collaborators, which includes Department of State, some local partners from some of the African countries. We have added more partners, including World Bank, the University of Chicago, Health Effect Institute. And then here is our team who has actually done all the works. I'm just presenting on behalf of them. Salman and Susan, can you raise your hand, please? They are here, and Alkma somewhere. So they have all done great work. June is not here, but thanks. That's all I have.
Thank you. Let's invite all of our speakers back to the front. And let's start the Q&A session. Questions? Okay.
Great, that was great presentation. Thank you for the presentation, all the presenters. I have a question to the ZeusAI. So 2 questions I have. First one, that when you were comparing the token compression using the Tempo version 3, version 4, and you found that Tempo version 4 was easy to reconstruct after compression, and Tempo version 3 had more error. Isn't this a problem on the side of the compression? Because satellite data, I mean, it has uncertainty, but here actually you are compressing the data and then trying to reconstruct that. We cannot put the blame on the satellite data for this one.
Yeah, so that's a great question, actually. So probably if we had when we started tokenizing the version 3, we started going down this route of like, oh, we need to change our distribution, because what we were seeing was lots of high values, which turned out to be erroneous. And so we need to either cut these out or change our distribution somehow. So basically, if we had put more development time into that tokenizer, it probably would have worked eventually. But we found a much simpler solution was just to use the cleaner data set.
Okay. My next question is with respect to the fusion. So you are having the polar orbiting satellites and geostationary, you're doing the fusion, that's the data assimilation, and then feeding to the model. You must be having many pixels where actually you don't have both of them, geostationary and polar orbiting. And you are somehow kind of estimating it with a complete gap-free image. For those pixels, are you also quantifying the uncertainty?
Yeah, so I didn't include the uncertainty evaluation, but there's a paper, it's Fendall et al. 2025, and it's the EarthNet paper. So if you go on our website, you can take a look at that paper and see the complete validation of the model.
Okay. And I have one question for Bryan. I really like the part that you want to bring the ozone source and sink in the model, not just estimating it, also bringing the source and sink, and you want to bring the hydroxyl radical to see that how. But I want to understand that how will this process go? We don't have the actual measurements of the OH. You want to see that how OH is reacting and contributing in the ozone formation or as a sink. How will this mathematically go in the model? If you can explain that.
Yeah, okay. So we're training on a model OH, a simulated OH. We don't actually have OH observation.
Yeah.
Right. Yeah. There's very few. In fact, there was one NASA field campaign called ATOM where there were some limited OH observations. They have large uncertainty bars. So we can sort of validate our machine learning model that way. But other than that, yeah, we need NASA to actually fund instrument developers to work on developing OH models, OH instruments.
And how are you trying to integrate this in the form of reaction? Like you somehow try to bring the reaction in the model, or you're trying to bring in the loss function, the ratio as a constraint?
Yeah, so what we actually were doing, I have a paper on this in 2024 in ACP where I talk about, well, you have OH, you can use machine learning to constrain that with satellite data, but to understand the variations and trends of science is very difficult. At least I know like Nathan talked about new techniques to improve the interpretability of the machine learning. But can you repeat your question one more time? How do we
how are you trying to constrain, like how are you trying to bring the OH with and the impact on the ozone in the model?
So what we did is instead of just constraining OH, we started to constrain the chemical sources and sinks. So you have satellite up. So if you look at a chemical reaction, you have a K value, which is temperature dependent. Well, we have temperature observations from satellites, right? And then, for instance, let's say the sink term with reaction with carbon monoxide. Well, we have carbon monoxide observations. So we have KOH right there. So we can calculate that, and then we can do the machine learning on that quantity. And we can do that for all the source and sink terms, most of them, so that we can constrain over 50%. I don't remember the exact number, but it's over 50% of the sources in the sinks. I don't know the exact numbers. But that gives you a little more information from a process-based perspective on what's going on.
Thank you.
You don't look convinced at what I just said. So
no, I think I need to read into that paper to understand the process in detail. But I think you are trying to bring more species and see that how their concentration increase or reduction is impacting the ozone concentration.
Yeah, fortunately, we have satellite observations. Oh, excuse me. Fortunately, we have satellite observations of almost all of the chemical drivers of OH and of ozone. The chemical drivers of OH and ozone are pretty similar, right? It's NOx, and you can use formaldehyde and carbon monoxide and so on. All of these go into it. Yeah, but if you have any questions, reach out to me after you take a look at the paper.
Sure, thank you.
No, this is great. Thanks again. It's Elise, right? Awesome. Yeah, I love the gap filling stuff. For the different tokenizers, the vision transformers, I was just curious if those were each trained in their individual domains, or if there was one set of model weights that would provide all the tokens. Yeah, how was that set up?
Yeah, that's a great question. So the tokens are trained individually per sensor, and then they're all combined when we put them into the masked autoencoder.
Nice. And probably in like a self-supervised way.
Yes.
Oh, okay. Okay.
Or we can talk later.
The pre-trained. Okay, yeah.
Okay, so I'll be honest, I'm very new to the AI world.
Sweat.
I have been in traditional inversion modeling, and I started working on AI models 3 months ago. So
nice,
if you could
nice.
define self-supervised versus supervised, I can answer your question.
Yeah. No problem. And maybe, was there a paper on that?
Yes.
Okay, so
yeah,
I'll check out that paper. Yeah,
Yeah.
it'd be great to get a link for that. And okay, that's great. And then the distribution, yeah, does that work? Yeah, I think because it's the same architecture. It's just different model weights. So, and they're trained with the same loss. Yeah. Okay. So sorry, I just had to reason myself through the stuff. Yeah. Very good. Thank you.
Hi, thanks all. Libby Moore, data scientist at Environmental Defense Fund. I have been, this is a bigger picture question that I've been thinking a lot about in my own work, because I recently used an LLM to analyze a large unstructured text data set. But I also work for an environmental nonprofit. And so, of course, like we're thinking about the issue of data centers and air pollution that results from, training these models, and that a lot of these data centers, because they're coming online so quickly, have to turn to fossil fuels, or I shouldn't say they have to, but they are turning to. And so, yeah, so it's like kind of this challenge of like, we know that AI and LLMs can like help us solve air quality challenges. And not all AI is as intensive to train, like greenhouse gas and air pollution intensive to train as like certain types of AI, like LLMs are more intensive. And so I guess I'm just wondering, like, how do you all balance this like tension between the air pollution that's generated by AI and the potential of AI to like help us solve these? And I know that's a like really big and hard question. So yeah, no judgment. I don't want to be a party pooper, but just yeah, hoping you can help me think through these things.
Yeah, it's a great question. It's one that I've been thinking a lot about in using AI. So I'll take a stab at it. The first thing is, I don't think we should like ignore those impacts, right? I mean, those are real, and I think we as society need to think about how do we do that well. And I think there's some parts of that debate that could be better captured about, how are we building, what kind of generation are we building out? Who's doing the building out? What permitting regulations are required around emissions related to data centers? And so I think, I mean, the conversation is maybe headed in a good direction, but I hope that we can do a better job of thinking about that holistically from from the AI industry as a whole. One of the other pieces that I think about, though, is that I think what we're doing in the air quality world is generally a very, very small piece of what's happening within the AI world overall. And so I think, and what we're seeing is that many of the uses of AI are more efficient than what we would have done traditionally, right? So, with AI emulators, we're essentially, we're potentially doing things on orders of magnitude more efficiently than we would have. There's a couple of questions there. One is, does a thing becoming cheaper mean you have less of it or more of it, right? And so that's another question. But at least in theory, for what we get out of it, we're using less energy and potentially having less environmental impact from those. And so I think that's encouraging. And I think I'll stop there. Those are the thoughts I have.
I don't have much to say, but thanks for bringing that question. I was not thinking, definitely. But I think I feel like Nathan says, even if we are, let's say we are using AI to fast forward the processes, which numerical model was taking days to process, and now you can do it in minutes, right? Because you have this AI. So definitely we are saving a lot of energy in that way. That computer model was already running, the infrastructure was already using the energy and everything. So in some ways, I think we are saving energies. Now, yes, we have to create a new infrastructure that will require resources and everything. But I feel like this argument goes same ways as when we started using electric cars. People say, well, you need electricity to charge the battery, and ultimately you are using fuel some kind of. But I think it's question of efficiency. Are we becoming more efficient or not? I think that is where I feel like the balance we can make.
Yeah, okay. First of all, yeah, thank you all for the great presentations. I'm Vishal from Chicago. We're at a stage today where AI is continuously evolving, especially in terms of like architecture, the frameworks. So at a high level, you guys are at the forefront of all of this. How do you think about architecture updation? Because you mentioned process-based networks. You guys have foundational models that you're working on. There are graph neural networks. There's so much out there. How do you think about, making those changes in a practical manner as compared to, getting more data and just retraining? So how do you balance out the two?
Yeah, that's a really interesting question. I would say that um, so when you're at a smaller company, when you're not at, say, Google, who's able to train these huge models and incorporate as much data as they want, you have to consider what model you're using. And so when we're training models, we have to select models that both we can train and incorporate the data. So that is to say, like, you have to balance both. Yeah.
I think this question gets back to the point about transferability that I spoke to, and like how applicable is your modeling architecture to extreme cases, like extreme events, record-breaking events? How robust is your model to applications in new locations? Do you need to retrain it every time you go to a new location, or you have a new data set? How long does it take before your model's out of date because there's changes in the inputs? And I don't think it's a solved problem, really, right? I mean, you want to retrain your model as much as you can because things change, and it's nice to have the most recent information. But again, it's costly and involved, and costly not just in terms of training, but also in like labor and time and attention. So I'm excited about the direction that some of this stuff is going. I mean, the knowledge-informed architectures seem like they point in an interesting direction. There's methods for that are coming up to maybe reduce the required amount of data that go into model training using foundation approaches. But my sense is that it's not a solved problem of like, how do you build a model that you don't have to retrain as frequently as you can? Did you have?
Yeah.
Great.
Yeah, and I guess on top of like the time to training, there's also the time to inference, right? So sure, we'd all love to run diffusion. It works really well, but it's very slow. It requires a lot of GPUs at inference. So we're thinking about that trade-off as well, and that trade-off also affects what data we can use, because some of the satellite data takes a few weeks or months to be processed to level 2, and so for those data sets, we have to use level 1 if you want to build a model that is hourly latency. So that's something that we think about a lot, and you're basically designing a model that can forecast initial conditions within an hour.
Well, I'll just add a couple of things. One is, so we are mostly NASA do the research, right? So we are not actually in a business of operation or developing something which will run for next 20 years or 50 years, right? We are trying to innovate every time. So if there are new technologies, new tools available, we like to try and see whether it is improving our understanding or not. So that's one aspect. So based on our research interest, we will either continue using the existing tool or adopt the new tools and architect whatever is available. The second is we also want to make sure we can explain what is machine learning is doing, even though a great model comes up tomorrow and it promises that I'm going to give you 100% accurate result. But if I cannot explain it, why it is giving and what are the factors contributing, then I will be shy to use that. So I think as a scientist, those things are very important for us to, when we choose new model, new technology.
Thank you all for the
Well, thank you all for the wonderful talk and the inspiring case study. Perhaps I myself doing a lot of work on machine learning and AI for different downstream applications such as wildfire as well. So perhaps I can ask a fundamental question on behalf of all of us using AI and machine learning for scientific work. With the advancement of AI, we now witness a lot of change. For example, with the foundational model and also AI tools such as code AI provided by cloud, and it can automatically help you enhance your model and do the parameterization and optimize the machine learning. So basically, traditionally, if we enhance our model in terms of performance by 5% from traditional machine learning like the decision tree to the deep learning architecture, we will be so happy and see those work will be publishable. Now with the AI tools, it seems it can automatically, within 1 hour, it can enhance your model and automatically revise the architecture. And so I want to know, what do you think would be future like focus for us to move forward while working in this field? Thank you.
I can. Well, speaking as a scientist, I go back to what everybody has said here about interpretability, understanding what the models are saying and trusting them. That's so. How do we get to that point? I'm trying to explore that with my postdocs, but we're not the experts. Those people are the experts. They should tell us. Listen to them.
Okay, so I have a bias because I come from the traditional, like sort of inverse methods modeling. And so I think of a lot of the AI modeling that we're doing as not all that different from the inverse models that we've been using for years. In fact, I think if you could probably formulate it and express it in exactly the same way. So I think it's going to accelerate the amount of data that we can assimilate into our models, which is exciting. But I'm not convinced yet that the numerical models are not going to be used anymore. But this is something that they in the meteorology world they're talking about a lot. Are we going to get to a point where we don't have numerical models? And that's a question I'm not equipped to answer.
I'm going to come back to the work is still making a change, is driving action to improve people's health, reduce sources, and protect the environment, right? And how we get there is maybe going to change somewhat. But I think the fundamental problem is still figuring out what is it that we need in terms of the next thing that's going to help drive that change. And so, yes, we might use more coding tools, and that innovation cycle happens faster. But there's all the downstream parts. There's the operations. There's the decision making. There's the trust and evaluation. And so, if that piece is turning over much faster, that may drive more attention to those other pieces. But it doesn't mean that we've solved the problem as society looking to address air pollution. So, and we still have all the data limitations too, right? So, like NASA's got fantastic satellites that provide great data sets, and there's some satellites that hopefully will go up soon or will be developed in the future that will go up, and that's still going to drive new innovations with bringing in new data sets, right? Because these models, as good as a coding assistant is going to make them, still rely on sort of the imperfect data. So maybe there's upstream challenges to be addressed still, and downstream challenges to be addressed, no matter how fast we can iterate on our modeling architectures. So that's my thought.
No, I agree with all of you.
Yeah, thank you so much for the talks. I just like one last question, um, especially for NASA working on machine learning and AI. I was wondering if computing costs have been a hindrance to you, and not just about like the money that you need, but also like the architecture that you need, especially with this newer, bigger models.
The short answer is yes. We are always looking for more computing resources because we have really highly skilled machine learning people in our group. And almost every week we have this discussion, can we get more GPU power? And I don't know how to get that. But so far we are able to manage with what resources we have. But you're right, that is going to be main requirement moving forward. And I think NASA is putting a lot of efforts in ensuring that we have right resources to do our work in changing environment with so we have more data, more advanced model, which takes a lot more longer times to run and develop. So it's definitely a ongoing challenge, but I think there are steps taken by agency which should help us.
Okay, I think we are close to our time. Great discussion about the fantastic AI technique. And thanks again for all of our speakers, and thanks for every audience to join this session. So I think the HAQAST official meeting will end up here. And yeah, welcome to next HAQAST. Jenny?